So all this is kind of a recap from section 2.1, but now we're using limit notation and we're not estimating limits numerically or graphically. We can now find the limits algebraically like we learned in sections 2, 3, and on. So we looked at this function before. This is a function that describes an object in free fall after t seconds. And before we estimated it numerically, and we guessed that at 4 seconds the velocity was going to be 39.2 meters per second. And now we can verify that with this limit definition of instantaneous velocity. So our function's 4.9 t squared, and our a value that we're interested in is 4 seconds. So here's f of a plus h minus f of a over h. And when we simplify, we get 39.2 meters per second like we guessed at before from section 2.1. So notice that we can generalize this formula. 39.2, notice that that is 4.9 times 4. And if you look at the algebra done when you simplify for the limit definition, you see why. That 9.8 th that you get from expanding this term, the h gets factored out so that you can cancel it with the denominator, and you're left with 9.8 t plus 4.9 h. But then when you take the limit as h goes to 0, this term goes away and you're left simply with 9.8 t. So we can find a general formula for the instantaneous rate of change for this function and plug in any value of t. So we can plug in t equals 1, t equals 2. We can see the velocity at different points in time using this simple formula. Okay, so where are we? We've revisited section 2.1. We've seen that we can estimate the instantaneous rate of change by taking limiting values of the average rate of change. We see that we can estimate slopes of tangent lines with limiting values of slopes of secants. We've seen how to find limits of functions, right, and what that means graphically and numerically. And so now all this comes to the derivative. The derivative, really what we've been looking at in the last few slides here, is the derivative. But the derivative is the concept of estimating instantaneous change with limits on many functions, not just a position function or not just from the graph of a function and talking about secants and tangents. It has much, much, much broader scope. So here's the official definition of the derivative. This notation is read f prime of a, and it's the limit as h approaches 0 of this difference quotient, which we've seen again and again. And if the limit exists, we say the derivative exists. It's differentiable there is the terminology. Alternatively, we can use this other difference quotient. This is kind of more like the average rate of change formula. So we can use both of those formats. So let's go back to slide 10 for a sec. This says find the formula for the instantaneous velocity. So instead of saying that, we could have just said find the derivative of the function s of t. Same thing. So the derivative is also the same thing as the slope of the tangent line. So if you recall, the slope of the tangent line was the limit as x approaches a of f of x minus f of a over x minus a. Well, that looks familiar, doesn't it? That's the derivative. So before, when we were looking at slopes of secants earlier in this lecture, we used this format of the derivative. So when you find the equation of a tangent line, you just find it as you normally would with the slope point form, and that m is just the derivative of the function at the point A. So from our earlier example, we could have just used f prime of 2 or f prime of a instead of using the symbol m for slope. So like I said before, a derivative has much broader uses and applications than just instantaneous velocity and equations of tangent lines. If you have one quantity that's changing relative to another quantity, you can find the instantaneous rate of change in that one quantity with respect to the other, no matter if you have enough data, if you have a function, if it makes sense. So the point is it has applications in many, many, many fields.